Subject today is soil carbon sequestration, primarily looking at the use of soil carbon as a way of mitigating climate change by drawing down atmospheric CO2 and storing that carbon in the soils rather than the atmosphere, where it can do good rather than harm. The title is The Size of the Prize. Indication mean that we're going to try and look at how much soil carbon could realistically contribute towards the aim of mitigating climate change. Before I get too deep into soil carbon, though, I want to give a little bit of background in a few slides, because the background and context is really important to this. Now, the first background I want to give is, I think I'm starting to feel that one of the big reasons that there's so much inertia and unwillingness in the general population to really take climate change on as serious as it needs to be is that we talk about it in the wrong kind of units. When we talk about keeping climate change below 1.5 or 2 degrees Celsius, to most people, they're used to temperatures fluctuating vastly more than that on a daily and annual basis, and a couple of degrees doesn't really sound like a big deal, and maybe we can just adapt to that. So I'd like to introduce from a well-known comic, XKCD, the Ice Age Unit, IAU, and this kind of reframes these temperature changes in a slightly different context. It's done in humour here, but I think it's an important point. So from the middle of the Ice Age, the last glacial maximum, up to modern times or pre-industrial times, we've got about 4.5, maybe 5.5, somewhere in that region. It depends on how you define it and measure it, degrees of warming. That is defined here as one Ice Age unit. We're on track to go warm by another Ice Age unit this century, with more in the pipeline after that. And I think that sounds a little bit more compelling than talking about a few degrees centigrade if we reframe these in Ice Age units. So when we talk about mitigation of 1.5 to 2 degrees, what we're really talking about is to keep the world in a safe zone. We need to limit warming to probably no more than about 1/3 to 1/2 of an Ice Age. The second piece of context I want to give you is just a brief history of the subject of drawing down carbon from the atmosphere. Just over the last 10 years, that landscape has changed dramatically since I started looking at it. So when I started looking at the idea of how can we actually get carbon out of the atmosphere if there's too much, it was widely seen as a backstop or insurance policy in case we didn't manage to save emissions rapidly enough. So 10 years ago I did this study, I think, which also built into the PhDs, published in Nature Communications, looking at the potential of biochar as one of the technologies we can use to do that, and showing that if we really push out the boat and do as much as we can without impacting food security or other sustainability criteria, we could maybe offset around 12% of current global emissions of CO2. To reiterate, that was really seen as a backstop 10 years ago, which we're thinking about insurance then. Now, rolling forwards just a few years to the 5th assessment report of the IPCC, a few things really started to change in the way we understand climate here. One of the things that really started to emerge at that point is the idea of a carbon budget. So the climate system is hugely non-linear, but interestingly, a lot of these non-linearities cancel out conspire to produce a nice linear correlation between the total amount of CO2 emitted over time by humanity and the amount of warming you will expect to see. So we can generate quite accurate, or we can generate carbon budgets which give us an idea of how much we can emit before we will exceed a certain temperature threshold of warming. So to remain below 2 degrees of warming, the total cumulative emissions over the entire history of humanity and future emissions together needs to be less than around 800 gigatons of carbon. As of today, we've already emitted nearly 600 of that, which leaves us a budget of roughly 20 years of future warming. And bear in mind that this is the midpoint. There's a lot of uncertainty about that. So this is our budget to have basically a 50-50, a coin toss chance of keeping the climate warming below 1/3 to 1/2 of an Ice Age. So with that in mind, the scenarios, the mitigation scenarios in the 5th assessment report really started to look more seriously at negative emissions. And they started to bring on a very important role in the sense of two things. A number of sectors can bring down emissions drastically, but transport and agriculture especially, and livestock, it's very difficult to get rid of all emissions. So we're going to need some negative emissions to offset the ones we can't mitigate in those sectors. And also, it seemed more and more likely that given the tight carbon budget we have available, we're not going to cut emissions fast enough to really avoid an overshoot. So negative emissions are also going to be needed to provide an overshoot. So either in the energy sector after 2050, using carbon capture and storage with bioenergy, that's an unproven technology. So if that's not available or doesn't work out on that scale, that has to be picked up by the AFLU sector, agriculture, forestry, and other land use. So huge demand for negative emissions at this stage, not just as an insurance policy, but as a necessary part of a mitigation package that avoids too much warming. Rolling forwards just a few more years to 2018 now, we have the latest IPCC special report on 1.5 degrees of warming. And really this hadn't been looked at in detail before. Before this report, people have mostly been concentrating on what are the impacts of really high levels of warming, and no one had really concentrated on what small amounts of warming might do. And it turns out that many of the risks become important, widespread, and difficult to adapt to, even between 1.5 and 2 degrees of warming, which really adds an impetus to actually striving for even tighter carbon budgets than we previously thought we could get away with. So now, with the available carbon budget shrinking, partly because we're aiming for a more stringent target, and partly because we've gone on increasing emissions for the last several years rather than cutting them, we're in a situation now where negative emissions are taking on a new role, not only to offset hard to mitigate sectors, and not only to recover from a overshoot, but also we need to have them now in order to draw down emissions fast enough to meet these warming targets. So that's the background. What can soil carbon do towards that? So at the Paris meeting, the French government launched an interesting initiative, which is really designed more to start a conversation and get political traction on this issue, called the 4 per mil initiative. 4 parts per thousand, that's 0.4%. What that referred to was taking, if you add up the total amount of soil carbon stored to 2 meters depth in the world, and you divide that by the total emissions of CO2 currently for humans, it turns out that if we could increase current stocks to 2 meters of soil carbon by 0.4% a year, that would offset all emissions. Now, most people don't see this as a realistic target. It's more designed to get the conversation going and get political momentum behind this issue. But it's a compelling idea. There are probably limitations on what we can do in that regard. For example, this paper by Minasny in last year looked at the fact that probably we can't realistically increase carbon stocks down to 2 meters depth very easily. They talked in terms of 1 meter, which is still quite optimistic. And they also concentrated their efforts on managed soils because it's very difficult to achieve this in unmanaged ecosystems. But if we go to 1 meter depth in managed ecosystems, they came to the conclusion that soils still have a substantial potential to offset maybe 20 to 35% of emissions. Again, there are probably a lot of constraints about this. This is maybe a target to shoot for, but it's an indication that this is something probably worth doing, although it's unclear how far towards that target we can realistically go. I'm trying to break this down a little bit into the kind of methods we might use to build the soil carbon. Here's a paper by Paustian from the year before, Paustian et al. And one of the things that's striking about this is that if we look at the reduction or removal rates of CO2 for the different interventions we might use against the area of land across the world where you could do those interventions, there's kind of an inverse correlation, that the things that store the most carbon you can only do in small areas, whereas the things that have a less per unit area impact can be widespread. and scalable. So all of these, and to be honest, even the ones which may be smaller amounts of per unit area carbon, add up to an overall package where you need to take on board all of these to integrate into an overall strategy. Just for context, I'm going to add biochar on there as well, in a slightly different place to in the original paper. The original paper made a mistake on mixing up CO2 and carbon and put that bubble in the right place. But biochar, because it's very much more stable than other types of soil carbon, for the same amount of organic matter added to soils, you can actually store much more carbon in the soil, and you can do so over a wide area. However, it's more expensive, which is one of the reasons people are really thinking now about things that may be more scalable because they're cheaper and easier to do, whereas biochar is actually quite expensive. It may well come into its own as we become more incentivized with higher carbon prices to mitigate. But for the time being, people are really thinking about these scalable types of solutions. And I think this, and final, this is a meta-study which tried to look at the broad literature of the different types of ways of drawing down carbon and see where soil carbon meets. Fuss et al. Came to the conclusion here that soil carbon, this purple box here, it's got one of the largest potentials for carbon removal on the x-axis at one of the lowest costs on the y-axis, again indicating that it can potentially have an important role. I don't think they captured the full literature because in fact you can find estimates anywhere along this, from the 4 per mil people saying that it can offset all emissions down to a number of papers indicating that it really can't do anything. So the uncertainties around this are absolutely enormous, and yet the indication is there that it perhaps is worth pursuing. And finally, in terms of background, another paper which came out last year looking at natural climate solutions, just to put a bit more context around this. Although Fuss et al. Put afforestation and reforestation kind of lower in the potential than soil carbon. In this paper, in terms of the potential for climate solutions, in fact, reforestation and afforestation seem to be very much the largest, although a component of that is, of course, the soil carbon, which also needs to be accounted for in those. So that's the end of the background. So we're in a situation, really, where we've got a lot of indicators suggesting, one, that it's urgent to draw down carbon, two, that soils can potentially play a role in that, but we don't really know what the constraints are going forwards in terms of how we can approach this or what the limits will actually be. So one of the things we started looking at was putting with the Nature Conservancy a workshop in Chatham House in London together, where we invited decision makers from sectors including corporations, finance, development, farmer organisations, to try and investigate over a few days of workshops what are the real barriers that restrict how far we can go in terms of making progress on soil carbon, and what can we do in terms of finding missed opportunities and unlocking those barriers so that we can actually make progress on this. Now, I'm not going to walk you through all of the things that came out of the workshops, but there's a few points that are very interesting to make. One is that in terms of what was considered very low priority by people from these sectors were some of the things that much of the literature is focused on. Things like competition for biomass. Are we going to use it for soil carbon or for bioenergy or something else? These kind of traits, trade-offs between food security and soil carbon, co-benefits, need for subsidies. All of these things are weigh very highly in the literature, and yet they were seen as very low priority by people who are actually on the ground trying to make scalable soil carbon programs actually happen in the real world. Slightly more important were considered things like exposure of banks to agriculture. For example, in Africa, very little agriculture is financed through banks at all, so there's very little interest in supporting these through the finance sector. Issues of carbon tenure, who owns the carbon, who gets control for it. But really the high priority ones are the ones I want to focus on here. The things that came out, some of them were surprising. Obscurity. Soils are considered mysterious and dirty, which builds into a lack of awareness about them in the general population. that although we walk on soils every day of our lives, they're seen as an other world that people don't really have a good grasp or understanding of. And that's a psychological barrier towards engaging with them thoroughly. But some of the other things like farm value, we need clear success stories showing farms successfully building soil carbon and getting value from it. Again, similarly, we need a business case for investors, success stories showing how the investors are getting something back from investing in soil carbon. A roadmap, how do we build a roadmap if we haven't got all these success stories to point at? So this was a recurring theme, that we need we need some real good success stories that we can build a narrative around. Another very important one that came out is the concept of protocols and methods. If you're going to invest in soil carbon, you need to know whether what you're doing is working. And if you're going to pay people to do it, you need to be able to check that they've actually done what you're paying them for. Unfortunately, at the moment, most places don't have any methodologies, really. Those that do, they vary from country to country and place to place. There's no consistency, which makes it very expensive and difficult for international organizations to really engage in this. They have to have expertise in every different methodology. So some more consistency would be useful. But even more importantly is the cost of monitoring soil carbon. If we want to monitor soil carbon accurately, and particularly considering that we need to do it to depth, because what happens in the topsoil may not reflect what happens throughout the soil profile, we need to dig soil pits to at least 1 meter depth, take multiple soil samples from these, take them back to labs, expensively measure the soil carbon in order to generate results. There's new technologies in terms of mid-infrared spectroscopy that can reduce the cost of doing the analysis, but you still need a massive effort in terms of collecting and analysing samples from across the world, which it's very difficult to do this through remote sensing. You only see the top of the soil if you see it at all. Usually it's hidden by a vegetation canopy. So scaling up measurement is really cost prohibitive towards a lot of these efforts. So the need for low-cost methods is one of the things that came out as important, which is close to my hook because that's something that I work on. So background over. What have I been doing? So low-cost monitoring and verification. I've mentioned that it's very expensive to go out and collect samples and analyse them. It's my view that the only really cost-effective way of measuring soil carbon is not to measure it at all. It's way too expensive if you want to bring this to scale massively. What we need to be doing instead is using models to predict what's happening in the soils and drive those models with things that we can measure at scale cheaply and effectively. But we need better models to do that, and we need models that can use data that can input data about land management, crop cover, all the different parameters that affect it at scale using remote sensing or low-cost surveys. There's still a lot of uncertainty in soil carbon models, and so there's not enough confidence in using only modelling at this stage to go this route. But this is, I think, what we should be aiming towards. So we need better models that we can trust. So I've been working a little bit over the last few years. One of the things we're doing is trying to get a better model. I'm not going to walk you through it in too much detail, but I'm quite excited by some of the results, so I'll share a little bit. So in some senses, this looks a lot like many soil carbon models, that we have plant litter entering the soils, and it's ending up in microbes who return it to the atmosphere, and it's going through various pools in between. So much, so good. That's very much like a lot of models. The arrows in orange here really differentiate this, because we've got a dissolved organic carbon pool now, the liquid form of the carbon, which can move down through the soil profile. That's very important to have in models. Many of them do not. And the orange arrows indicate processes that soil microbes mediate the rates through their enzyme activity and their ecology and things like that. So putting in the microbial interactions that change the rates at which these happen allows us to have a much more mechanistically correct type of soil carbon model. Now, a number of people have been working on these issues, but it's been very hard to get good calibration to produce microbial explicit models that we really trust at scale. Many of them produce quite strange predictions, such as oscillations, or if you double the amount of carbon going to the soil, they have no effect. So there's been quite a struggle to get good models using this kind of approach up to now. So this model, here's some example of these are long-term experiments of over 100 years, up to 200 years nearly in Rothamsted in the UK. and measurements taken of soil carbon throughout those periods. And the model predictions track over the long term very, very accurately with an R² of about 0.92 for these. That's in itself quite promising. If we try to run the model at the global scale, again, mapping out soil carbon, running the model like this, the predictions in red against estimates of maps of soil carbon in the open boxes, again, track very well, R² about 0.93, I think, 0.9, between the soil carbon stocks in different biomes around the world. So again, it's performing very good. And I think this is quite an important one in terms of really trusting these models, is that it's not enough to just predict the stocks of carbon, but it's very important to be able to predict the age of the carbon to get a sense that we really understand them. If you go down through the soil profile, what you find is if you dig down a metre, soil carbon is often thousands of years old there, and that's been very hard to replicate in the past with models that don't have pools which are artificially extremely inert. But we know that this very inert carbon doesn't really exist in the soils. Whereas this microbial model is also able to replicate very accurately the age of soil carbon going down to the profile. So this is really a step forward in being able to trust models, to be able to roll them out scalably as a way of trying to predict soil carbon and use measurements of remote sensing vegetation cover, MPP, management, this kind of thing, to drive the model to get predictions we can trust at a price we can afford. So the second thing that came out of the workshop in London, where we're trying to get priorities, was the recurring theme of a need for success stories. And so I'd like to share with you one of the success stories that I've had the luck to work on, which is a study we did for the World Bank in Ethiopia. So in Ethiopia although it has a fast-growing economy now, it's suffered massively from food shocks and famines over the years, and it has a perennial problem of very large-scale food insecurity, where a large fraction of the population, typically over 10 million people, just simply do not produce enough food yearly to be able to support themselves and their families. And they are highly dependent on food aid coming every year. Now over the years, this dependence on food aid was not being alleviated by the aid programs that were just keeping people alive but not lifting them out of poverty. So there was the development partners of Ethiopia and the Ethiopian government got together to try and put together a food security program that really tried to address this by trying to use the food security program to alleviate some of the actual causes of poverty, the underlying structural problems that are causing people to be perennially in poverty. And there are a number of areas that they target with that. So as well as giving food and cash transfers, they sort of mix that into both disaster risk management, but also infrastructure investment. So trying to build infrastructure as well as at the same time as just giving people aid in order to build resilience and build the economy. But importantly for this, there was a lot of investment in trying to use some of this program to rehabilitate degraded lands through a number of different soil and water, climate smart agriculture and SLM type practices. We'll see some of these in the coming photos, so I won't walk you through the list. It's important to recognise that this program, when it was designed and envisaged, had nothing to do with carbon, certainly nothing to do with soil carbon. They were trying to protect the productive capacity of the land in order to improve the livelihoods of people. So they have massive erosion problems. Gully erosion is rife through the croplands. The topsoil and the soil is being washed away at an enormous rate, and soil degradation is a real problem now and also threatening the future food security of the country. So this was really seen as a way to address this food security issue through a food security program. So this is just one photograph of one of the types of areas we've worked. As you see, the land degradation issue is absolutely incredible here. There's almost no vegetation remaining on this. This is still grazed. The cattle are just bones on this side of the river. And it's just it's a horrific condition with gully erosion and very little topsoil left on much of this. It's been grazed down to the bone. Whereas On the other side of the river there, you can see an intervention where they've, what's most obvious from the distance here is the trees, but it's actually a much more complex system than that. So they've got, as well as forest regrowth, particularly in the riparian zone, they've got a lot of cut and carry forage, so livestock are excluded, but they can still cut and take grass out from the system, feeding the livestock on that, and actually getting more forage out of this system than this degraded side on the other side of the river, which is equivalent in all but being in a different different district which doesn't have this intervention. There's also agroforestry systems mixed in. There's non-timber forest products such as gum and bees, that kind of thing. So and this is typically what we see throughout the PS&P system in terms of the interventions, is these multi-use land changes that try to both provide value to the local community while also avoiding some of this terrible sort of land degradation. So we did a large-scale study travelling all over the country, thousands of miles on very poor roads to some quite remote places, and give you just an indication of some of the types of systems we've seen here. Up in Afar, in the Upper Rift Valley, we've got, again, a very degraded system, soil carbon very low in these. We can compare it to the native, there's a nature reserve not too far from here, which has not been grazed heavily, which is almost like natural conditions. And the difference in soil carbon is phenomenal between this and a natural system. And here's a farmer-led intervention where they've excluded livestock, but they cut and carry hay. And the soil carbon is already rapidly, over a few years, building up towards not reaching the levels in the native system yet, but still a lot better. There is a proviso attached to that. When we think about soil carbon, we need to be very careful to also consider that it's part of a whole package of emissions from that sector. So this land that they've sectioned off is also much more productive in terms of forage than the overgrazed land outside, which means that they can increase their stocking density, which in turn means that the methane emissions from the cattle they have go up. So in fact, in this particular system, any benefits from soil carbon sequestration in terms of climate change are negated by the methane emissions from the cattle that they manage to feed on the improved forage. However, that's not that's something you need to always bear in mind when people talk about pasture management as a way of sequestering carbon. That if you're improving the pasture and you're not probably going to do much, what you need to do as well is reduce stocking. At this point in time, there's not really any way around that we need to reduce livestock as well. So there's a huge conversation to be had about how that affects food security. In countries like that, the opportunities to reduce stocking are very limited, whereas in the developed world, they're enormous. There's far too much meat consumption. So if we look closer to home, I think we can certainly think in those terms. Here's another example. This is on a steep escarpment, for example. This is rich cropland at the top of the escarpment, which is gradually eroding back from these, which has become destabilized and massive erosion from the cropland above into these. So the building of vast arrays of terraces and foresting it. You can just about see from distance here the terrace is growing up here and the vegetation starting to come back. Close-up shot here. Again, the soil carbon growth in these is quite phenomenal. Here's a very different type of system, which is a mostly cropping system, but we've got legumes across the soil buns. We've got a lot of trees mixed in, mixed-use forestry and agroforestry mixed into the system, cut and carry forage, orchards, irrigation, and a very complex system to model, a lot going on there. Here's a agroforestry system. Again, this is just one little bit of it where you can see an orchard, but there are many types of cropping systems built into this. Here's a tree planting, so they have actually tree nurseries in some areas where they're trying to where natural regeneration is not happening fast enough, the land is so degraded, where they're actually replanting at scale with digging holes in order to capture moisture in these very arid environments. And this is just one example of an intervention which actually doesn't store carbon, it does the opposite, because we have to accept that that happens sometimes as well. This plant here is Presoak, which is an invasive weed. It's extremely thorny. It's taking over large areas of traditional rangeland, and it's hated by the local pastoralists because it's too thorny to walk through. They're in danger of wild animals and snakes in the area, and it's very difficult for the animals to feed on it, although the pods themselves are very nutritious. They're well protected by big thorns in these large thickets. So a lot of the intervention in this area goes towards eradicating Presopis, which actually has roots down to 10, 15 meters, which is why it stays green even when no other plant will, even in the most arid times. So it stores a lot of carbon, and when you eradicate it, you're undoing that. However, it's still a popular thing to do there. So we travelled around, we did in many of these sites kind of extensive surveys, mapping the different areas of different land uses, doing collecting data on what types of management, what crops, what fertiliser regimes, how they're using crop residues and manures, et cetera, on different croplands. Also on adjacent places outside of the project areas to do soil carbon measurements to get a sense of business as usual versus the project. And what we saw, I guess no big surprise, is really that the biggest potential for increasing soil carbon is absolutely on the forest, agroforestry and perennial crops. Although we've got some beautiful examples of cropping systems that are extremely diverse and they're full of very innovative ways of building up the fertility of the soils and building soil carbon, it's the nature of annual cropland that it's much harder, much more challenging, especially in a tropical climate, to build soil carbon very rapidly. So we saw less impact on the soil carbon from the croplands, although the fertility impacts of the cropping, of the sustainable cropping systems they put in place were more profound. But and grasslands, this is net greenhouse gas balance. Again, we didn't see a lot of impact, largely because of the issue I talked to you about before, which is although we're building up soil carbon in these improved grassland systems, often that's at the expense of increased N2O and methane emissions from livestock. But overall, if you extrapolate the projects we looked at to the scale of the PSMP, the Food Security Programme in Ethiopia, it's despite not having any intention to be a climate mitigation thing, it's already contributing around 1.5% of the country's nationally determined contribution towards the Paris targets. So even though this had no intention of being a climate mitigation project, it's already sequestering 3.5 million tonnes of CO2 a year, which is very substantial. And roughly 40% of that, about the same amount is in biomass, is going into the soils. So soil carbon is really an important part of the success story here. And I think that's a story that can be told more widely in order to show the importance of this. And this was, of course, also backed up by measurements we did in the field. Soil profiles dug at many of these locations around, both outside the project areas and within project areas, to try and measure the differences. And again, that backs up very much the idea that these interventions are building and have the capacity to build a lot of soil carbon if they are invested in for the long term. Now, I'd like to acknowledge some of the co-authors and some of the studies I looked on this. In alphabetical order, not in any other order here, we've got James Amanet of the Department of Energy, Bahano Belay and Jimmy University in Ethiopia, Steve de Gloria here, Mark Easter, Colorado, Stephen Joseph in New South Wales, David Lee is in the audience here, Johannes Lehmann, Edna Milne, Dawit Solomon and Elaine Strick-Parrott, Swansea, and also the funding I've had from NERC in the UK, World Bank, USDA, DOE, and the Atkins Centre and the Nature Conservancy. So finally, before we open up for questions, I'd like to sort of leave a thought about this, which is we've seen that that drawing down carbon from the atmosphere is extremely important. We have very little hope at this stage of actually addressing climate change adequately unless we can draw down a lot of carbon. We've seen that soil carbon may have a potential role in that, which could be very large and could be very scalable because of the low cost, although the uncertainty around that remains massive. So I think what we've seen from the high priorities from people who are actually trying to scale up, actually on the ground trying to scale up these things, is that the ultimate size of how much we can achieve is not the most important question right now that we need to be focusing on. The question is, what is holding us back from making progress now? We have to start somewhere. We have to start making steps towards, even if we don't know what the end point is. We know that soil carbon is valuable. We know that we can build it, and we know that there are challenges right now that we can address. And I think that some of the literature which is focusing on the big scale long term of where, how much can it really do? Is it worth doing? That's the wrong way of thinking altogether. Every bit of carbon we store in stores is progress, and we need to start pushing forwards and understanding the potential more as we move forwards. So how much can we do? The maximum potential is probably the wrong question. We need to know what are the untapped opportunities at the moment, what can we do to boost these, and what are the barriers, what can we do to overcome them. And we've seen that there are success stories out there. They just need to be made more widely known and help to build a narrative that pushes forward the agenda and actually making this happen at scale. So thank you. I'll leave you with some of the pictures of some of the things we looked at in Ethiopia as part of that success story, and then I'll open up for questions.